Now for part 7. Alas, we're ready to prove the division property of exponents for rational numbers, after a brief discussion of the power of a quotient rule for radicals. We aren't doing a formal proof, but it's possible to do one. Essentially, the quotient rule for radicals is derived from the rule for exponents. Consider the first orange bullet. We have a over b to the power of m, which equals a to m over b to m, because the exponent can be distributed to the numerator and denominator in the following way. In the last orange bullet, we can extend the rule to rational exponents. The terms in the blue box should look familiar if you've watched the previous video. As a result, the quotient rule for radicals in the white box, read as the nth root of the quotient a to the m over b to the m, naturally follows from the quotient rule for rational exponents, the blue box. Alright, this is not a proof, but let's do a brief walkthrough from the white box to the white box. But if we need to, this is a scratch work for a proof. The first white box, by the quotient rule for exponents, can be rewritten as the nth root of a over b to the power of m. Recall the definition: the radical as a rational exponent is for any positive real number x. Then we can let x equal a over b. We know the right-hand side equals a over b to the power of m over n. See that? Next, the first column. We know the right-hand side, the quotient rule for rational exponents, is derived from the left. Lastly, in the second column, the blue box can be rewritten as the radical expression over the radical expression. We can simplify as the nth root of the quotient a to m over b to m back to the white box, which is the quotient rule for radicals. If we were to do a proof of the quotient rule for radicals, we could refer to the definition of radicals as rational exponents. We already did a study in the previous video. Now the proof. Division property of exponents for any non-zero positive real number a and any rational numbers n and m, such that a to the n over a to the m equals a raised to the power of n minus m, labeled red asterisk. We'll refer to what we just discussed in the previous video, the definition: radical as a rational exponent, and the division property of exponents for integers, the blue asterisk. We'll extend it to rational exponents. That being said, in the first column, we let a to the n equal a to the k over p. Then a to m equals the following for any positive integers k, p, s, and r. Then consider the second orange bullet. We times the first rational exponent by r over r, which is the same thing as multiplying the term by 1. Then we multiply the second exponent by p over p. The second column, ladies and gentlemen, substitute the exponents with the adjusted rational exponents. Next, we use the definition of the blue box to rewrite the numerator and denominator as radicals. Nice. Observe the third column, first orange bullet. We use the quotient rule for radicals, which we just discussed, to put the entire term under the radical symbol. Second orange bullet. We use the blue asterisk to rewrite the term under the radical because kr and ps are just integers. What naturally follows, we know just implies the blue box. The last orange bullet. Distribute the denominator to both terms, shows the operation of subtraction is defined between both terms by a common denominator. So, the term on the left-hand side can be rewritten as a to the power of n minus m, because n and m are any rational numbers. The white box holds. Therefore, the division property for rational exponents is proven. We're done. Very nice. At first, it might not be obvious we needed to use the radical, but we absolutely needed to, because the radical notation allowed us to apply the division property of exponents for integers independently. and then taking the nth root of the term under the radical symbol, which is well defined, in this case, taking the perth root, allowed us to return the exponents back to rational ones, essentially and logically extending the division property of exponents to rational exponents. Furthermore, it's obvious, the rational terms need a common denominator in order to subtract. Therefore, as a consequence of the continuity between the radical and rational exponent notation, the entire operation shows the division property holds for radical expressions and rational exponents. And the inverse in action again.